So today, midterm, you'll get that. Probably we want to know what the scores mean. So before we put too much thought into them. So midterm one back, and then we'll move into ancillary statistics. This is the next thing in your book. The next thing we'll do after this is the likelihood principle, and we'll probably wrap up chapter 6 with that. There are a few other things to say. Complete statistics, I will introduce you to what they are tomorrow. It will not help you to answer any statistical question, but it's an interesting phenomena. I'll try to at least front load that today when we talk about ancillary statistics. There's nobody that'll ever ask you if your statistic is complete. So, just real quickly, does anybody know what an ancillary statistic is? Anybody know? I'm sure somebody knows. Anybody feeling daring and want to give a definition for what an ancillary statistic is? Let's just use a little bit of English language. I like words. What does it mean for something to be ancillary? Somebody says, you're arguing about something, and somebody says, oh, that's ancillary to what we're talking about.
Tangential.
Yeah, it's tangential. So it's actually maybe orthogonal, you might think, but that is a tangent, right? So I kind of like those words too, that if I'm looking at the tangent of a circle, I'm looking for, where a line is 90 degrees to the radius of that circle. So yeah, I think that's right. So it's like tangential. That might be a little too connected for us. So, but it means that on its own, the statistic doesn't provide any information about the parameters. So let me just say real quickly, and then we'll go through an example and understand the nuance here and why we're even talking about this in the first place. This is kind of a weird one because this is a stat that has no information on its own about the parameters, where a sufficient statistic has all the information about the parameters. So it's kind of in some sense the opposite. A statistic S of X is ancillary if the probability distribution or the density, so whatever that means, it could be a CDF, it could be a PDF, both things will happen, it doesn't matter. So the distribution of this thing right here, where I'm thinking that the x's, xi's, are coming from some distribution that depends on this parameter theta. So I can rederive a new distribution. This is just a transformation of variables. So I'm somehow transforming it. I've got a collection of these things. So the x's are just the x1s to the xn's. This doesn't need to be IID or anything, but we might think about IID examples just to make our life a little bit simpler. But this distribution, when you end up taking the transform and you work through this probability distribution, this thing does not depend on theta. So what that means is that that statistic itself you cannot use on its own to tell you anything about theta. So it doesn't have anything about it. It doesn't have any information about theta. Let me give you an example, just real quick before we jump into the midterm. So say I've got x is distributed, let's say x1 is distributed normally with mean mu and variance sigma squared. And let's say x2 is normal with mean mu and variance sigma squared. These don't actually have to be the same sigmas for this to work out. But if I told you this, x1 minus x2, if I asked you to work that out, the difference between these two things, you might notice this does not depend on mu. Very good. So the difference of those two things, because they're both center at mu, if I take the difference of them, I lose the information about mu. Shift parameters are like that. So if I take a difference on two things with the same location parameter, I knock out that location parameter. So that kind of makes some sense. What about this? The ratio x1 divided by x2, this might be ancillary for something. We don't actually lose the information about where mu is. They're still centered at the same place. Does anybody know how this is distributed? There are two normals. A normal divided by a normal. Any guesses? What's that? So if somebody says F, what do you think about F as an answer? This is, first thing I always do is I just check to see what are the bounds of everything. So an F distribution is always positive. So is that thing always positive? No. So not an F. So that's the first sanity check. So not a chi-squared, not a gamma, for all the same reason. This turns out to be Cauchy. And it doesn't depend on the sigmas. The scale parameter gets knocked out. So if I have a scale parameter, let's just imagine I was going to rescale this. Let's get rid of that and just make this a 1 for a second so that you could see this. If I ended up multiplying this by sigma, both of these random variables right here, this is now normal, this thing, with variance sigma squared. So in this thing right here has variance sigma squared in here. So sigma times x2. So it just changes the scale. It's a scale. Look at what happens. Those cancel each other. It's that simple. So scale parameters, if I take ratios of things, I knock out the scale information. And that kind of makes sense. So that's what rescaling something does, and now I knock out the scale by dividing it out. So scale parameters come through multiplication, so to get rid of them, you work through a division. Location parameters come through addition, and so to get rid of them, you move through subtraction. So we could work out what the distribution of that thing is. You probably wouldn't do it real mathematically. You'd probably say, I already know what normals are, and the difference between normals is normal. And it's the difference between their means, and I add together their variances. So, and this one you might have to work a little harder, but at least you could come up with an argument without working through its distribution and deriving that that's Cauchy, that if I multiplied this by a scale parameter, they would cancel each other out. And so that would be a very easy way to work through this problem. But in general, if you didn't know what kind of parameter something was and what the nature of that parameter is, you'd have to work through its transform distribution and show that it doesn't depend on theta. So that means that if a statistic doesn't have any information about that parameter on its own, so I keep saying that same thing, it might have information in the presence of something else. So, and I'll try to distinguish this. But ancillary statistics on their own don't tell you anything about theta. So if you were Fisher back in the 1930s and you were trying to understand this newly evolving field, statistics, as an actual field, you probably wanted to find what are properties of statistics. So I think from an abstract point of view, this is a really interesting question. It's when do statistics have information about parameters, and when do they lose information about the parameters? So if you're trying to understand as a field, and not necessarily just how to do data analysis, but you're thinking about it a little bit more abstractly and generally, this is an interesting question. Here's another interesting question. Are ancillary statistics independent? And you might be thinking orthogonal. So if you want to adopt a new rule, a new word, orthogonal, that's when they are independent, when they live in entirely different spaces that don't overlap each other. That's when you get independence. So I sometimes like other words. So are ancillary statistics independent of, let's say, a min sufficient statistic? there's a question that we can motivate. And so if we went back to Josiah's word, it's tangential, it's orthogonal, you might be inclined to say, yeah, they are. They live in different spaces. But the answer is not always. So, and this is something that Fisher figured out for us. And so it depends on the day of the week when I talk about Fisher, whether or not I really like him or if I don't like what he did. And just like most people, there's a little bit of both in there. So he's a human being. So we don't like everything, but we don't hate everything either. So Fisher is one of my top 3 statisticians just for this reason, that he went through all of these questions and tried to understand what is the relationship between different statistics and how they provide information. So I think this is a really good question. Turns out the answer to this is, if the min sufficient statistic is complete, then they're orthogonal. And I'll say something more about that tomorrow. That will never help you to do stats or anything like that. If you're working with sufficient statistics and you're conditioning on it, you're in good shape. Please.
So when we say independent, are we talking in terms of distribution? Or
yeah, do they factorize?
And what is the motivation behind ancillary stats?
Just what I told you. If you were Fisher and you were trying to think deeply about what are the properties of statistics, so if you were to ask the question, how far could I compress the information down and still have all the information about theta? A natural question? I don't know. Maybe it's not. I never know what people mean when they say natural. But an obvious question, once you think it's obvious already, might be, well, what's the opposite of that? When do they have no information? So I think that's the motivation. From an engineering perspective, pish-posh doesn't help you to do anything. From a mathematical perspective, you could see getting really excited about these things. So it kind of just depends on the hat we're in. So I see it both ways. I see it as, we could just get rid of the ancillary statistics, not teach anything about it, because it doesn't help us to do anything. You know, but because we're really deeply entrenched and interested in statistics, we want to know all this stuff. That's what this class is about. So kind of all the underpinnings, all the things you want to think about. When is there information, when is there not information? This has never helped me to do stats. And I would say probably when I was a grad student, I was like, get rid of this theorem. We don't need it. This is Basu's theorem. It discusses the complete statistic and when ancillary statistics are independent of min sufficient statistics. But now, I feel a little bit differently, that I'm like, it's interesting. Does that kind of make sense? Okay, we'll come back around to this. Let's look at the midterms. I do have these. I'll hand them back at the end of class. Here's my one rule. So we can discuss. We can debate the scores. If you go to your friend and they have 1 point more on some problem, you can come to me and I'll either tell you why I marked you off that 1 additional point, or I'll give it back to you. And very often I say, okay, since we've had the discussion and you understand, I give it back to you. I don't really care. You know why? It doesn't make any difference. I will never change your grade off of 1 point. So it's very easy for me to just take the line and move it back 1 point. So I'll never do that. My lines aren't hard-coded. You'll see what I mean in a second. I will give you the opportunity to do makeups on the midterm. And so let's imagine you got a 50% on the midterm. And so you're panicked because of it. You can redo the entire midterm for me. So what you want to do is write out the problem pretty neatly, write out the solution pretty neatly, make sure that it's clean, it's good, and you're going to give it to me in a week's time. So I'll probably say a week from maybe this Friday or something like that. So a little over a week. If you give it back to me perfectly, i.e. 100, which you should, I'll give you back 50% of the points. So 50%ers can move up to 75%. So I apologize to those of you that are going to be like, I got a 99. I can turn back this thing for a half point. My recommendation is do not worry about it. That will not affect you. I'm going to make it so that we just don't give out a lot of bad grades in this class. Okay, so I get to decide how big the gap is between a B plus and an A. Things like that. Jake?
And that's in addition to the Metropolis extra credit thing?
In addition. Yes. So lots of ways to make sure you can still get a good grade in this class. And the midterm is intended to point out things where you need to strengthen up a little bit. So does that make sense? So let's look at the scores. So I did all of the scoring. I even went back twice over it to make sure I was relatively consistent. Today, no questions can be asked about the midterm. So, or I mean, you can ask casually, but I'm not going to debate scores with you. I don't even want to look at it. But if you have some curiosity, of course, I would answer your question. On Wednesday, however, we can open it up. So I just want you to go home, sleep on it, think about it, and also think about what the important points are that you're supposed to be learning this information. Okay. So also, just a note, we'll do a review on Wednesday. And this is at 5:30 p.m. It'll be here. So I think that's a good time for it. We have a homework that's due on Friday as well. So we'll do review session. And if you have any questions about the exam, that's a good place. Even though I'm going to say things like, well, I want you to figure out the last couple details on it. I don't mind if you're really confused. We can clarify that. But I still want you to struggle through this because that's when you learn. So learning and struggling, they're exactly the same things. So struggling is good. They tell you that? So you're supposed to suffer. So suffering is good. So I'll just mention also on the web page, I did put up extra credit assignment. There's one more link down here. It'll take you to this page right here. I've typed up very clearly what the Metropolis algorithm is. I've given you a problem you can employ this on. So this will be Metropolis sampling for two parameters, mu and the inverse of sigma squared. So that's the precision parameter. I like thinking about it this way. I'm going to put this into a Bayesian framework, although you could employ Metropolis in a non-Bayesian setting, but we'll just do it in the Bayesian setting. So you're going to be working through a posterior distribution that looks like this. So the prior on mu and phi is 1 over phi. If you want to know why that is, you would take my Bayes class, or ask me during a review session, why is that a really good prior choice? I'll say a little bit more about that in chapter 7. So the book hasn't even gotten to Bayes yet. And so I'll try to address some of these questions as why is this the right prior to use? What it's basically saying is that your prior on mu is flat. So it's perfectly flat, so there's no information about the location put into that. Turns out 1 over sigma squared, or 1 over phi, or 1 over sigma, if you transform all of those things into each other, those are exactly the same distributions. They're all improper, meaning they don't integrate to unity. So they integrate to infinity, but we don't care because Bayesians only care about the posterior. And priors drive properties of their posteriors. I'm going to at least say it that way. It makes me sound like an objective Bayesian. So let me just clarify, I mean that very subjectively. So here's a posterior distribution. It's not normalized. You will simulate data out of this normal distribution to get those x's, and then you'll do MCMC to try to learn mu and phi. So you'll apply this algorithm. I want you to tell me what the proposal distribution is for this. You can use that symmetric random walk for a problem like this. It works really well, but it does not work well on phi because phi can't go negative. So if you have lots of questions about which proposal should you use, I'll happily tell you during review session. So that might be a good place to talk about this. I will also offer you, this is 10% midterm credit, so read through it before we go into more detail on this thing. I'll give you 10% midterm credit for doing this problem. I will give you 5% midterm credit if you go to that homework problem where they have you trying to sample a Cauchy out of a normal, If you code up that metropolis sampler and show that it doesn't work well in the tails, I'll give you 5% midterm credit. If you give me the fixed up solution to that problem using a better proposal, i.e. maybe use the random walk proposal, if you use it on that problem, I'll give you 5% more. So that's already 20% midterm credit. And if you go to experimenter 2's distribution for that normal distribution that we studied when we were discussing sufficiency, and you run metropolis on that example, I'll give you another 5% midterm credit. So there's 25% midterm credit, and you can just decide how much of it you'd like to get. You can also get 50% of the differential credit from your exam score from 100. I said that really weird, but you know what I mean. Okay, we can come back to this. This is just supposed to make you feel calm that there is stuff you can do to improve your grade. If you're willing to learn more stuff, I'm happy to keep teaching and give you points for it. This will be due at the final exam. So you have all the way until the end of class to do this, and I'll probably give you one more extra credit assignment as well along the way. Okay, midterms. I've run through the scores and I added everything up and I put it into my grade sheet. What would you like to know about the scores? I'll tell you anything you want to know.
Mean and median.
Okay, mean. So this is very predictable. Mean, 83.7. So I'm going to try to wean you off of this. So the mean. So I know that you have been trained and indoctrinated to ask about the mean, and I know there's instructors that even use the mean when they come up with their grading procedures. I had my physics professor when I was a freshman in college said mean is a C, and you need 2 SDs over to get an A. So every SD over is a letter grade, which is totally bizarre. So to even think normality has something to do with the grade distribution in the physics class. I was really miffed because we had our first midterm and I got a 20 on it and the mode was a 20. So we all had the mean, so I had a C. That's a really good way to unnerve a student. I'm still pissed. So I did get an A in that class. So, but there's, I guess. So anyway, people do look at the mean. SD, so square root of the variance of midterm 1 scores. So if we did this, the highest you could get is a B if we used my old professor's grading scheme. That's not the case here. So anything else you'd like to know?
Can you give a 5-number summary?
A 5-number summary. What do you want?
Like the
1,
min,
4,
interquartile
9.
rate. No. Min, first quartile, median, third quartile. Maps.
I guess. We could make a box plot of this.
Yeah.
Box plot. Midterm 1. Just really thinking about that, huh? Is that what you wanted to know? I've never seen anybody want just one box plot. I usually eyeball them and look at them next to each other, the side-by-side sort of thing, and I can compute the p-value for you if you wanted to do the f-test and do ANOVA and see if distributions are the same. If I compare this to different years, this would absolutely be different. So my typical trend in this class is a bimodal distribution. A lot of people near the top, a lot of people somewhere below, and then some stragglers down to the left. Over the last 3 years, not including this one, so at least the last 2 times, it's become uniform, is the distribution that I've been looking at. So it's like the troughs started to bleed together. You guys weren't communicating with each other and sharing information and forming those natural cliffs. This is certainly not uniform either. So there is a difference here. And I was thinking about it all last night. Why? And I have all kinds of reasons. I don't know if any of them are true.
Is it histogram?
Yeah, the histogram, right? So just show me the distribution. Yeah, get rid of this thing. It's why not, you know, glance at that, but how about this? There's my histogram. I obviously messed with that right there, and I said I wanted 2 bits in here. So histograms look, histograms are a little bit weird to look at too. There's a histogram. Let's do the default. You must like 10 for a reason. So there's 10. So they like 10 because we have 10 fingers. It is that. That is the reason. There's all kinds of arbitrary decisions we make that have to do with we have 10 fingers. How much money we spend, how we round, how far you'll run. Like, oh, I need to do 10 miles. Can't be 9.6. So you'll do that extra jaunt around the block, right? So, means you're OCD, be careful. We all are. Okay, so that's about the histogram right there. So it's skewed to the right, heavily. So I kind of like that the tops are performing pretty well. Over here, we can look at this a little bit coarser if we wanted to, kind of see where everybody is. I think this is about the same view. So when I look at histograms, I usually look at a couple different resolutions when I'm glancing at these things. But lots of people over here, so that's good. People making minor mistakes, really tiny stuff. So for example, I did mark people off one point. If I said, how do you use the delta method to estimate something? And if you gave me g of theta hat is distributed according to this distribution where I need to know what actual thetas are. And I plug thetas in, that's the statement of the delta method, but it's certainly not how we use it. So for example, how you might use it on the simulation assignment. So instead you take all those thetas and turn them into theta hat. You'd have e to the normal, e to the theta hat, comma, g prime evaluated at theta hat squared. So that's e theta. The derivative of e theta is e theta. So e theta squared is e2 theta. You got to plug theta hat in there to call it something. If you're going to estimate with it, it needs to have estimators in there. So I mark off one point for that, just as a reminder so that you know what the word estimation means. Estimate this. Use the delta method to estimate something. The theoretical statement of the delta method doesn't tell you what to do with it. So but when you plug estimators into it, so i.e. you pivot, now you have something that you can use inferentially. I.e. you can estimate with it. So that would be a -1. I don't really care, I just want you to be aware of the word. So if that helps you to remember the word estimator or estimate, then I'm happy with that. So that's what, you know, the difference between some of these are. Minor problems. I would say, looking at this, these are all A's. So what I do is I look for natural breakpoints. So I'm never going to have a grading scale that's like an absolute 90, and if you get to 89.9, I'm like, yeah, I'm just reporting the news. So, because it's not that, right? I graded it, I did all of that. I could make it as hard as I want. And it all means different stuff. So I look for natural breaks in clustering. I will do this across all of your midterms, all of your finals. I'll look at where you lost points. What I'll do is I will not grade your midterm until I give you your final grade. So as I'm sitting there and I'm looking at your final grade, let's say you have a B+. And then I think about how you took that grade, and I look at it, I look at plots for all the different midterms, and I go, oh, you missed one problem on midterm 1, and that really messed you up. You know, you took 25 points of a hit on that, which was pretty significant. I will go to your corrected exam, I will look at it, I will add those points back, and if it lifts you up over wherever I've drawn the thresholds, I will give you that grade. If there's somebody that has done worse than, or a little bit better than you on the original midterm, and you did extra credit and you end up hopping over that person, I'm going to take that other person with it. So if it's real close. So sometimes you'll be helped by other students doing well. So I'll never use extra credit to push people down. That's what I'm saying. So that doesn't become the new high bar. So it's something different. I don't think I've said all that before, but it's good to get accustomed to this. So I would say these people right here, so there's a few of them, and I can almost tell when I grade the exam what's going on. I think those people could easily be in the next group up. And I think it is just a function of reading the book. So reading the definitions, I saw a lot of confusion, mincing concepts in the definitions, not sure what exactly you're supposed to show, but probably relatively simple stuff. So the minimal sufficiency question, a lot of people use just show the factorization theorem, and that doesn't show minimal sufficiency. So there's a definition for minimal sufficiency, and some of you may have forgotten what it is and how to demonstrate something is min sufficient. So you'll look that up and address that yourself and get clear on that concept. But I think that problem on min sufficiency, it's in the book. So it's right there. And so it tells me just practice. Read the book, those things do work. So finding solutions online to problems is very easy to do. So nowadays it's so easy that it's killing you guys sometimes. So it would be much better if you struggle through the problems and actually work lots of examples, work all the examples in the book. If you did that, I would guess all of this stuff would get crunched right up there. So again, no secrets getting there. It's just practice. So I would say these students over here, I would guess with extra credit and the midterm makeup and all of that, there's no reason you can't still get an A in this class. So I would say if we leave it where it is, and we don't do all the extra credit, I would think a B plus or an A minus is still attainable without doing all the MCMC sort of stuff. Just turn in the corrections on that, and I think you can get close. I would think that if you kill it on the next midterm and the final, there's no reason everybody can't get an A in this class. So I'd say now is the time, though, to kind of change, do a course correction, and start reading the book and working through problems, working through all of the details of problems. And if you don't know something and you don't understand it, come and ask me, ask each other, but be really honest with yourselves. Do I understand all of the steps? And I promise you that after a couple years of doing that, you'll get really good at this stuff. So it's just the way it works. You cannot not get good at something by practicing. I said that weird too, but you know what I'm saying. Any other questions about this? So I was relatively pleased with this distribution. I just think about how do we get everybody over here up there. And I think there is a pathway for that. Okay. Any other questions about this? Any other questions about how I'm going to grade once I have all of your materials? Everything I do that seems like it's outside the syllabus, I draw lines, it will only help in terms of the grade. I will also say it's very easy to get an A in this class and not really understand all the material. So there's a big difference between getting an A and getting it. So I think you can get about halfway there and still get an A. So if you want to be a card-carrying statistician and be the person that people call up when they need a statistician to check if a statistical argument is correct or if the details are correct, you'll need to do better than just get an A in this class. So you'll need to be studying this stuff all the time. I'll just point out, probably all of the faculty members here, and this is probably true across all colleges, all departments, is even when we don't have homework, we work problems. So read the books, different arguments, because we want to know the material. So, okay. This is just helping us to keep pace. Okay, cool. We'll go over the MCMC a little bit more next time, and I'll write down what the 3 different assignments are. Here's just one of them to get you started. So this one's worth 10%. There's another one that's worth 10%, and there's another one that's worth 5%. And they're all MCMC variants. If you can work through this problem, you can probably work through all the other ones, and it's not too much of a challenge. You don't need to do this. If you already have really good grades or something like that, I think that's okay. I put this stuff in there because not all of us are good at sitting down in a classroom and taking a test. Some of us are just a little bit better at implementing things and doing projects. At the end of the day, if I were to have you guys do anything, it would be able to give presentations on real data sets and things like that. So if you're able to give a presentation on something and talk about it really well and make it interesting, that's the holy grail. That's what we're aiming for. So this kind of pushes you more in that direction. So nobody will ever pay you to sit around and do a bunch of homework problems. That's just practice. But you should do it. Okay. Good. Let's do ancillary. This example is very similar to the example that we confronted earlier in the semester with the range and the mid-range. It's going to be a little bit different. So just a small difference. This example is in your book. So let's look at this. Xi's come from a uniform distribution. And this is going to have parameters theta and parameters theta to theta plus 1. So the min is theta and the max is theta plus 1. Just keep in mind this example is very similar to what we did before, except this was 0 and that was theta. So the range was a little bit different. So I'll just point out, if I were going to look at the range in the example of a uniform from 0 to theta, the range tells us about theta. Kind of makes sense, right? It's telling us about that right endpoint. Basically, xn, the maximum, is telling us about theta. So the range is kind of like the maximum, especially if x1 is estimating 0. And so we looked at a lot of different estimators for a problem similar to this, and this problem is not too different. So this is a uniform that's always got unit length right in there. So incredibly similar. Make sure we know this is all IID stuff. Let's just say we collect X. X1 down to Xn. So we collect n data points, and we're able to form the range, which is the max minus the minimum. And we can look at the mid-range as well. So same sort of setup, except that we just changed the bounds just a little bit. So let's just look at a few things real quickly. We know that the xi's live between theta and theta plus 1, and this is true for all xi's. And so we know that this means that the minimum is going to be greater than theta, and we know that the maximum is going to be less than or equal to theta plus 1. So already we're kind of treating this problem a little bit differently, that the minimum seems to be maybe a little bit more useful than it was in the previous problem, because the bound is defined on both the left and the right hand side. So what that means is that theta is going to be less than x1. That's just this. So I haven't done anything fancy to it, but I can take this and rewrite it a little bit and write down that xn minus 1 is less than or equal to theta. So this is this, xn minus 1. So we know that. So all useful stuff. So we might write down then our distribution f of x, and I'll write down this is given theta. This is going to be equal to the product. I goes from 1 to n. I've got these little delta functions where the xi's are between theta and theta plus 1. And I end up dividing this by 1 because it all has unit length right here. So in the earlier problem, we'd have divide by theta there. The density is 1 over the unit length, or the 1 over the length of the interval, but this is all unit length. So we can just get rid of that right here. So, and this would just be equal to, if I just looked at when is this a 1 or a 0, I could just write this down like this. That this is going to be, theta is going to live between xn minus 1 and x1. So, same exact thing. So this is the likelihood right here. I will point out that on the midterm, on some problems, people would magically sometimes get correct answers because they would throw away the thing that they weren't supposed to throw away. If it didn't make a difference, and you would have got the right answer anyway, I marked it off very subtly. But I pointed out to you, you need to include those indicators. So, because they have the theta in there. And that's kind of the whole thing. So keep in mind, this indicator is the whole likelihood function right here. It tells us everything. Let me just ask a question. So we know xn and x1, the minimum, max and min, are sufficient. Here's my question. Are they min sufficient? I'll let you think about it for a while. Let me just draw you a picture of what this density looks like between theta and theta plus 1. And I've got some data points in here. This one's xn. This one's x1. Are they minimal sufficient? What do you think? What's that?
R is minimum sufficient.
What is?
R.
R is?
Minimum sufficient.
It is.
I think because their in-cause directions are the same. Excellent.
Let me just ask the actual question that I'm asking. I don't want to say what the answer is to yours, but you might want to rethink that just a little bit. So is x1 and xn, those could be formed to create R. So R is a function of other minimal sufficient statistics, or other sufficient statistics. Minimal sufficient statistics are functions of all of them. So in terms of that, that's true. I did use these two things that are sufficient to give you that. But that doesn't mean on its own that that does have all the information in it. What do you think? Is that insufficient? This would be a fair game midterm 2 question. Or qualifying exam question. I consider it an easy conceptual question.
Should the indication function of the value of xn and x1?
Yeah, I'd have to give it to you, right?
I think I will value.
Yeah. So I'll let you think about it a little bit more. So not give you the answer. But Yeah, we do know that if you have xn and x1, you've got all the information there. Question is could you make it any smaller? Let me just ask you a different question, just while we're at it. Just to show you all the nuances in these things. It doesn't take much to change a question and change everything about it. If I have this, xi uniform minus theta to theta, we know that the minimum is estimating that. The maximum is estimating that. So are the min and the max minimal sufficient for this problem? The answer is no, that it's whatever one is farther out there in magnitude. So if I take the absolute value, it's only the biggest one in absolute value sense. So is the same thing true here, or do you actually need both values? The answer might be yes. They might be min sufficient. So, okay, let's not dwell too much. Let you think about that some more. Let's work through what we would have done last time. I'll just give you what the answer is. So I think we already have done this problem, or at least all the steps to understand this problem. If I wanted to understand the joint distribution FR and M, given theta, this is n times n minus 1 r to the n minus 2. It works out exactly the same as we did last time. So something's different about the bounds though. R goes between 0 and 1. So that's a little bit different, where before the range went between 0 and theta. That was the only thing that was different here. Now R goes between 0 and 1. And the mid-range is going to be theta plus r over 2. I would ask you, how do I know that off the top of my head? I wrote it in my hand, just to make sure that I get this right. This is actually the exact same thing as we got before. Had something to do with this r over 2, that was the slope. But I'd probably have to work through the drawing again, just to show you all this stuff. Again, this is all in your book. This is going to be theta plus 1 minus r over 2. So this is a little bit different. These bounds are the hard part of this problem, and that's what you'd have to work through. Again, on a midterm, I've never asked you to do this. So I don't want to confuse you on geometry or anything like that. There won't be any trig transforms or anything like that. So, but this is the whole thing. So note, if I ended up working through the marginal distribution, this is just the integral n times n minus 1 r to the n minus 2 dm, and this is going to go between theta plus r over 2, theta plus 1 minus r over 2. That's pretty easy to work through. N times n minus 1 times r squared times theta plus 1 minus r over 2 minus theta minus r over 2. This minus that. This integrates right here to just an n, and then I take the difference between those two things. So this theta cancels that theta right here, and then these two add together. So this is going to be 1 minus r. So minus r over 2 minus r over 2 is minus r. So this does not depend on theta. R lives between 0 and 1. That's still true. So there's no thetas here. Does not depend on theta. So the range is ancillary. And that's how you verify that. It just doesn't have theta in there. And we can kind of see it. In this particular problem, theta is a location parameter. It's sliding around this uniform distribution. So The range doesn't tell you anything about location parameters. It tells you things about scale parameters. Think about the other problem, uniform 0 to theta, that's like a uniform 0, 1 times theta. But it stretches that right-hand point, so that's a scaling parameter. And so the range definitely tells us about scale, but the scale here is given to you because we know what the interval length is. So this problem's a little bit different. We'll come back next time, look at a very similar example so we can kind of see what's going on, and I'll distinguish this phenomena for you that I think if what we've said is the range doesn't have any information, but xn and x1 have all the information in there. And so if I gave you the midterm, if I gave you the mid-range, what would I actually be giving you in return? I'm giving you information about both of those data points in the presence of R. So we are telling you something about those two data points, x1 and xn. They are min sufficient in this case. And so R on its own doesn't have all that information, but in the presence of M, I can use it to get it. And so it turns out this is not a complete minimal sufficient statistic, and so it's not orthogonal, and it does have some information in there. I'll come back next time with a discrete analog of this example, and we'll flush through what I just said, be real clear about it. And then we'll be jumping into, I think, the likelihood principle, and then I'll circle back around and tell you what complete statistics are. So, okay, midterm back. So just go digest everything that I wrote. If I made an error, come to me very peacefully and let me know, and we'll get through it. If you're worried about your exam grade and what your final grade is going to be in here, there's no reason to worry yet. Just start doing some extra credit work or work through your corrections on this. Emerald? Welcome back, everybody. Just a couple of reminders. We'll do a review session tonight at 5:30 in this room. So review tonight. I think the homework problems from the book were relatively easy this time. You know, nothing super hierarchical. So relatively easy, but some of the stuff still takes some thought and possibly you have some confusions about it. So you can come and ask questions about that. We also have our project that's upcoming and due. So simulation study, so if you have any questions about that, that would be good. We also have midterm. So if you have any questions about that, you can ask that. Just a quick reminder, you can redo your midterm, write it up very clearly, and I'll give you up to 50% of the differential between 100 and your score. So for example, if you got a 50, the difference between 150 is 50, I'll give you 50% of those points back for correct answers. So I'm almost looking for keys out of all of this. If you do hand it back, make sure you do all the problems in there, even if you've done them correctly. So I'm looking for perfect assignments. So that's how we get good at things, is we just practice what we're supposed to be doing. I was going to say something else about that. Anyway, just a reminder, those are due next Friday. So I'll say next Friday. So not this Friday, so in just over a week. Midterm corrections. If you got a 96, please don't. So, but if you are that neurotic, feel free to. I'm happy to give you 2 points back. So it won't make any difference, but if you need to do that, that's okay. Also, we have some extra credit that's out now. And there's 2 other kind of similar extra credit problems. If you want to ask questions about that, tonight's review session is a really good time for that. Any review session is a good time for that. And I always try to make some room for office hours as well after classes. So if you have questions, there's plenty of time to ask them. Any questions about that? So today we're going to finish up ancillary statistics. I'm going to tell you what a complete statistic is. I'm going to tell you why it's incredibly difficult in most cases to show something is complete. I did give you one assignment on it. The solution is in the solution manual, and if you guys are like all my other classes for the last 10 years of teaching this, you're going to have solutions that are really similar to that solution manual. That's okay. So what I want you to glean out of that is that it's hard to prove something is complete because you have to show something happens across all functions out there, and that can be a difficult thing to prove. The nice thing is that Basu's theorem doesn't actually help us to do stats or to do inference. It's an interesting curiosity. So when is there any overlap in the information between a sufficient statistic and an ancillary statistic? So on one hand, sufficient statistics have all the information about the parameters, so you can't get anything more about the parameters with your sample than what's in the sufficient statistic. That's true for a minimal sufficient statistic as well. And an ancillary statistic on its own has no information about the parameters. So an example, last time we worked through this, we worked out the marginal distribution of R, and we showed that that doesn't have any dependence on theta. So R itself doesn't have information about theta. You could work through all these details and derive that distribution and come up with those triangular bounds. Do all of that stuff. Or you could just kind of notice that that's a location parameter right there. And if you take the range of a location parameter, it's not telling you where it's centered. It's telling you about the spread of the distribution. And so we saw a different problem that was similar to this, uniform 0 theta, and theta was acting as a scale parameter. And so the range tells you about scale parameters. So there's a little bit of intuition behind this, but then you can formally show that that doesn't depend on theta. I was asking basically this question when I was in your shoes of why do we care about ancillary statistics? What is the point of all of this? And basically I've come up with my own answer to everything, is that if you're interested in properties of statistics, this is an interesting question of when can you squeeze some information out of an ancillary statistic? There's a branch of statistics called the conditional frequentist. So conditional frequentism. Now I'm not going to go into it because it's really hard to figure out which ancillary statistic you need to condition on, but it's a branch of frequentist statistics that conditions on some ancillary statistic and gives you good answers. I'll say a little bit more about that in my base class, just to kind of overlap some general material that we're missing here, but I'm not going to go into any great detail about it because there's no paradigm for actually doing it. So there's just examples out there, a couple examples that if you conditioned on something ancillary in the presence of something else, you might do better. So than just a fully asymptotic answer. So make sure your answer is conditional and not asymptotic. I kind of like that. There's another way that you can be conditional for free, and you don't have to do any of that, and that's to follow the likelihood principle. That's what we'll go into next time. Basu's theorem is just a statement about if a minimal sufficient statistic is complete, and we'll go through that definition real quickly. All I'm going to do is just show you the definition. I'm not going to ask you to work out any of that on a midterm or a final, so you don't need to prepare yourself for that. I just want you to add this to your vocabulary so that you know what people are talking about if they introduce a complete statistic. Saying that, it probably doesn't help you to do anything other than answer the question of when is a minimal sufficient statistic in an ancillary statistic living in tangential spaces or orthogonal spaces, i.e. they're independent of each other. Okay, let's go through a simpler example. We're going to study this example, but in discrete case. This example is also in the book. It's kind of in paragraph form, so let's break it down. So here's a discrete analog. So probability x is equal to theta is equal to the probability x is equal to theta plus 1 is equal to the probability that x is equal to theta plus 2. And all of these are going to be 1/3. So it's a uniform distribution across x on 3 different values. So if you wanted to just impute values right here, maybe you could think of theta is 3, so this would be 4, this would be 5, for example. And so it's just a uniform distribution on 3, 4, and 5. That's all that is. So very similar to the other problem. Hopefully you can see theta is acting as a shift parameter. So, and we're just dealing with 3 points in the space. Okay, so we can consider, I'll say 2 data points. You could make this n, it doesn't really make any difference, but I'll just consider 2, x1 and x2. They come from this sampling distribution. Now let's just make it n. And we can compute the range. So the range is going to be xn minus x1. And there's a few different possibilities. Hopefully you can already see the range is an ancillary statistic. This looks just like the other problem. So this is kind of what we do as faculty members all the time, is we take problems that we know and we change them just ever so slightly to see if you understand what the points were. So this would be a good example of that. So the range is ancillary. We kind of know this from a previous example. So the question is there any information in the range? And as we know, on its own, the answer is no. There's no information about what theta is on the range on its own. But we also know that we've got this other test statistic, the midrange, xn plus x1 divided by 2. And we know already the likelihood function for this problem has to do with just the max and the min, just like the other problem. So the max and the min were the minimal sufficient statistics, i.e. they're sufficient. I will point out in Basu's theorem, even though we haven't stated it yet, there's a statement about minimal sufficiency in there that says if a minimal sufficient statistic is complete, then it's independent of all ancillary statistics. The minimality of it doesn't matter. So the statement is still true without it being a minimal sufficient statistic. There's just a caveat that if a minimal sufficient statistic exists, all complete statistics are minimal sufficient on their own. So it happens automatically. You don't need to chew too much on that. Again, it's not going to help you to perform inference any better. So in 5 years, when you're bored, sit down and study this maybe. So that's about when I got into it. I remember being able to go through the proof and thinking over and over again, when would I ever use this? So I guess that makes me an engineer in some sense. So anyway, it depends on the day. Okay, so these are minimal sufficient for the problem. And we're going to show that the range does have some information in it. So let's just work out all the different possibilities. So the range can take on one of three different values. The range can either be 1, that is if I solve this or that together. So then the range would be 1. The range could be 2, that would happen if I solve this and that. Or the range could be 0, that would be just repeated sampling from the same distribution, from the same, getting the same instance twice. So the range can take on 3 different values. So the range could be, I'll say, 0, 1, or 2. And then we're just going to work through the mid-range. Look up at which values the mid-range can take on. So the mid-range can take on 3 different things here if the range is 0. So if the range is 0, I could have seen this twice, or I could have seen that twice, or I could have seen that twice. So this is going to be theta plus theta divided by 2, that's case 1. Or I could have seen theta plus 1 plus theta plus 1 divided by 2. Or I could have seen theta plus 2 plus theta plus 2 divided by 2. Of course, averaging the same thing with itself just gives you the same thing back every single time. So these each happen with probability 1/3. So each one of those things happens with probability 1/3. You can think of it like this. I'm going to sample one thing the first time, no matter what. Let's say I sampled this, that 3. What's the probability of sampling that 3 again? It's 1/3. So I sample something with probability 1. What's the probability of matching it? Probability 1/3. So these each happen with probability 1/3, each of these 3 events. So I could infer what theta is based off of this. Maybe I could say something like the mid-range is either going to be theta plus 1, or theta plus 2 with probability 1/3, and that happens for all 3 of these. So it tells me a little bit about something. Let's see how this changes as I see different ranges. So if the range is 1, there's 2 different ways that I could have seen this. I could have seen this and that, or I could have seen this and that. So either I saw theta and theta plus 1 divided by 2, that's the mid-range, or I saw theta plus 1 and theta plus 2, and that's the mid-range. So this is going to be theta plus 1/2, and this will be theta plus 1. Each of these happens with probability 1/2 for the exact same reasons that everything before happened uniformly. So this will be the mid-range, will either be theta plus 1/2 or theta plus 1. And these each happen with probability 1/2. And this is probably the most compelling case right here, that we actually know things with certainty. So this, let me just write this over here. So when the range is 0, or sorry, the range is 2. That means that I saw this and I saw that right there. So this is going to be theta plus 2. That's the only possibility. Divided by 2, this is the mid-range. And this is going to be theta plus 1. And so that means that the mid-range is equal to theta plus 1 with probability 1. That's the only possibility. So if I did see the range and it was 2, and you happen to tell me something about the mid-range, or if I worked out the mid-range and it was whatever this number is and it's the only possibility, then I could tell you what theta is with certainty. So just be really clear about this. The mid-range minus 1 is equal to theta, guaranteed. So with prob 1. So the range does tell us something. So there's some information in there, but on its own, if I just gave you the range, you wouldn't know anything about theta. But if I gave you the range with the mid-range, some other information, then you can start saying things about theta, and you could maybe even be certain about what theta is. So this is the thing that motivates Basu's theorem. So what Fisher is thinking about, at least I guess this is what he's thinking about, is you might have thought that ancillary statistics should have no overlap with the minimal sufficient statistic. And that's not always the case. And so Fisher is compelled to think about in what cases is the ancillary statistic independent of the sufficient statistics. And the actual statement of Basu's theorem says minimal sufficiency, but it doesn't matter. That's not used in the proof. So all complete statistics are minimal sufficient if they exist. We won't prove that. Okay, so here's the question. So the question is, are ancillary stats independent of, and I'll write in minimal here, but you don't need this, minimal sufficient stats? And the answer to this is maybe. Here's at least an example where there is some overlap between two things. So if you want to see an example where the minimal sufficient statistic, let's say I'm trying to do inference on mu in a normal example, you might figure out that if you had s squared or something like that, it doesn't help you at all to answer the question about what mu is. So if I gave you sum of the xi's minus x bar squared, divide by n or n minus 1, whatever your favorite number is. I personally don't care. If you use that statistic, you cannot get any information of mu out of that. And so one thing we know is s squared and x bar are independent of each other. And so we could have figured out that x bar itself was complete. We won't do that. So there's another way through the problem, is you could just show that they're independent if you wanted to know that. So, or you could work through a more exhausting exercise of showing that it's actually complete. The book does that for you if you want to look at that example. Okay, so maybe the more precise answer is if the sufficient statistic, then I'll say the minimal sufficient statistic, although you don't need it to be minimal, it just so turns out that you can make this statement. If you can make the statement about sufficient statistics, you can make the same statement about minimal sufficient statistics. So the sufficient, if the sufficient statistic is complete, then yes. They're independent. I could see this being the whole entire field of statistics, answering questions like this in the 1940s, but nowadays we have real problems to solve. So we don't dwell too much on this stuff, and we give you more practical things to do. And apply all this knowledge to something. And so in that sense, this is probably not that interesting because there's no application for Basu's theorem. Let's just tell you what a complete statistic is. I might say a few things about it. But on a midterm or a test, I might ask you for the definition of complete statistics. but that's it. So I just want you to know what this definition is. So let's say, I'll use the same notation as the book. Let t equal t of x be some statistic so it's a function of all the x's. Same notation that we've been using all semester. So I'll just use this shorthanded notation, but when you're thinking of t, it's a function of x's. So what makes t random? The x's make t random. So if expectation of gt, this will be conditional on theta, there's some theta in the problem. So I'll just remind us, xi's are coming from some sampling distribution f of x on theta, given theta. So same theta. This is a function of x's that depend on theta. So if you wanted to use probably the notation I like using a little bit more is plugging the x straight in there. So the book just decided not to do that. So if this is equal to 0, and this implies that the probability, or I should say p if it's a density function. If it were a mass function, I would say probability p of gt is equal to 0. And I get to know theta for this, so probability problem, gt is equal to 0. So what this says, if the expectation of gt is equal to 0, then the probability that gt is equal to 0 is 1. So let me say that a little bit looser. If I expect for gt to be 0, then gt is 0. And this is for any function g. So for all functions g. So what that means, if you're going to show something is not complete, you would find some function where this expectation is 0, and then you would show that that g is not 0 itself. So if you wanted to show something is complete, then I have to do this over all functions g. So that takes a little bit more mathematical ability to start arguing over all functions g have this property. And there's a homework assignment with the solution manual solution. So you can follow that for turning it in. I just want you to at least work through one problem, or at least look at one answer to a problem of how you show something is complete and see that it can be arbitrarily difficult. So if somebody shows me some test statistic and shows me what the model is and asks me if it's complete, I have no idea. So I have to sit down for a couple hours and try to argue it. So I don't have any shortcuts. It's not like the factorization theorem where I can just kind of do something in my head and check real quickly whether something is sufficient. So this is much more difficult. So here's kind of the idea in all of this. This expectation, let's just imagine we're in a continuous space. So I have gt right here, and then I'm going to integrate this over ft given theta. dt is equal to theta. So this f is a little bit different than that f right here, so I'll just remind you, this is the f corresponding to x. This is a transformation of variables. So I have to do some transform to get the transform distribution on t. You could work through the actual x's and plug these in, and then work with the probability distribution of x and not do the transform. That's another way to do the problem. They say the same things. But basically, you have to come up with the probability distribution of that test statistic and work this thing out. So what this is saying right here, this condition, is basically checking independence of things. Think about what we do with vectors when we're trying to check to see if they're orthogonal to each other. We take a dot product between those two things. So I've got a vector x and y, and I want to know, are they orthogonal to each other? I take x transpose and I multiply it into y. And if it's 0, then they're independent of each other. They lay in orthogonal spaces. That's what this is saying. So it's just averaging over that same concept. So it's just checking, is this dot product right here, i.e. replace that with a sum if you're thinking about these as vectors, and showing that they're independent of each other, i.e. they're tangential. They're orthogonal to each other. They're independent of each other. So that's kind of the idea in all of that. So of course you have to check that in every space, in every transform, they're also independent of each other. So that's the hard part. So turns out, if this condition is true, then your minimal sufficient statistic or your sufficient statistic is independent of all ancillary statistics. That's Basu's theorem. There's a page or two of math in the book. If you really want to read through it, you can do that. So, but I'm not going to test you on it. So Basu's theorem says if a stat is minimal sufficient, you don't actually need the minimality in this, it just needs to be sufficient and complete. Then it, so I'll say a stat, I'll call it T, X. Instead of saying it, then T of X is independent of every ancillary stat. The only reason I'm telling you this is that if you're hanging out with students from a different school and they have to work through complete stat problems, you at least know what they're talking about. And then you can say, yeah, but when does that ever help you? And they'd say something like, well, it helps me to get a good grade on the test. And that's about it. I think it is an interesting question. I think it deserves a little bit more credit than I'm giving it. So, but you have to be thinking about this through a mathematician's lens and not a, what am I going to do with this result? And here's the reason I think that. Because I like to follow something called the likelihood principle. So I get everything for free. So let me tell you a little bit more about that. Before we switch gears, are there any questions about this? So here's the definition. And it turns out, if a minimal sufficient statistic satisfies this definition, it means that it's independent or lives in a different space than every ancillary statistic. Why is that important? Because if you're Fisher, you might be thinking that they live in different spaces automatically and there's no overlap between those two spaces. It turns out it's just not quite true. And we've seen an example where it's not quite true. So there's a little bit of information, but you have to add something to it to get anything out of it. Okay. Let me tell you what the likelihood principle is. Let me make a few notes about likelihoods first. Let's do this. Reasons to like likelihoods. I will mention, and maybe next time I'll bring a passage from a book, there was an argument that took place between, who was it? Oscar Kempthorne, I.J. Good, and Dennis Lindley. So does anybody know who those people are? Anybody know who any of them are? So Oscar Kempthorne, anybody know his name? So he was the advisor of Boyd Harshberger. Does anybody know who he is? Founder of this department. So Iowa State guy. So design and experiment guy. He was arguing with Lindley and Fisher and I.J. Good, and they were all doing it here, about likelihood functions. And that some people don't subscribe to using likelihood-based inferences. Nowadays, nobody argues about that. Everybody uses some form of a likelihood-based inference. Even the Neyman Pearsonians do it. But they do it in a way that violates the likelihood principle, and we'll talk about that when we get to it. But likelihoods, I don't think, are contentious at all anymore. Keep in mind, what is a likelihood function? I take the sampling distribution, I plug the data into it, and then I think that there's information about that function as a function of the parameter space. And it tells me relatively how likely different points in that space are compared to each other. So you're using the exact same functional form, the same connection between the data and the parameters, but you're flipping what's fixed and what's in a function of. So you're using that same functional form, that same connection between theta and the data, that same form between the data and the parameters, what you want to learn. And for me, that just kind of makes sense. That what else would you use? So if I already know this functional form, this relationship between the data and the parameters, I should be able to use that to do inference. So kind of makes sense. So people want to make a stronger statement than that. I'll tell you what the statement is. I think that it's a little bit overly strong and there's no actual proof of the likelihood principle. So we'll talk a little bit about this for a day or two. But let's just write down a couple reasons that we might like likelihood functions. So I know why I like them. Why might you guys like them? What's not to like? It's called a likelihood. It's the most likable function out there. So I tend to say likelihoods are the driving force of all good inferences. So even if you didn't go that route, there's a likelihood-based inference that matches your inference. So if you have a really good inference and you derived it somehow, I can match that inference by using the likelihood function. So that's not the likelihood principle, that's just my version of it. I believe that's true. It's a good way to irritate everybody, is to say, oh, well, you've derived it wrong. Here's the right way to think about this. So, but Bayesians did this for a couple decades and kind of pissed everybody off. So I'm willing to tone it down so that we can at least bring up people over and say, I don't care what you do, just use the likelihood function. Why are likelihood functions so good? What do they do? This is kind of the statement about the likelihood principle, and the example that I'll give you is what can go wrong if you don't use the likelihood function. And that's probably the most compelling argument for the likelihood principle, is these examples that show you what can go wrong if you don't adhere to the likelihood principle. No reasons. Think about the conversation we were just having. This is the whole class. So why do you like things? Why do you do stats the way that you do stats? There's reasons. It's not just because, oh, it's a formula in the book. You know, we use this formula. They do that in Stat 101 to us. You know, they tell us all kinds of nonsense too. So it's true. So things that are just not true. So like pooling variance estimators and saying that that follows a t-distribution, false. It's not true.
Can you use likelihood function to estimate factors?
Yeah, we can use likelihood functions to do estimation. What properties do those estimators enjoy? So that is the question. Why do we like likelihood-based estimators? Josiah.
I didn't have an answer to that, but I was just going to start drawing something out, which is that I've always used likelihood because it's like using the sampling distribution. It just feels kind of into like we're going to make this assumption about parametric, like, I'll follow this distribution, and using the likelihood just feels like, to think about the parameters just feels like it makes sense.
That makes sense to me too.
That's not very
Yes. What do you guys think about asymptotic stats? Saying things like, well, as n goes to infinity, this is good. You like that? I mean, sure, it's a good sanity check. So the only thing I ever like about that argument is it tells me when I'm just blatantly wrong. You know, that if I take this concept to the limit, you know, if things do not go the way that they should, if I have all of the data in the world and I do not converge to the right parameter, my estimator doesn't converge to the truth, then I know that I'm doing something wrong. So, but in terms of saying things like as n goes to infinity, we could assume that this is normally distributed, I think that that's not useful to me because I want to know how big does n really need to be. And I know what my sample size is. So I've got a sample size of 34 data points. And somebody gives me some theorem about n going to infinity. So it doesn't help me. It might. So if you're the type of asymptotic frequentist that I usually encounter, they usually don't even check the assumptions or tell us about the constants, the asymptotic constants and how quickly it's converging or anything like that, because it's really hard to do for an arbitrary problem. And so what you need to do is simulation studies, really, to be able to validate that what you're doing is even good. But that's not the culture, is to show you up front, I validated this model. And every talk I've ever gone to, they just have a model out of thin air. I usually ask them, what does n need to be before those asymptotics kick in? And they'll say something like, I don't know, you know, relatively small. But the number actually turns out to be like 10,000 if you check it. So I would say they're not a real frequentist. They're some sort of fictitious frequentist. So likelihoods don't do that. Likelihoods are fully conditional answers. So they conditional on your actual sample and your actual sample size. So they condition on the actual sample. As opposed to using the n goes to infinity argument. Think about our prelude to Bayesian analysis. There's two ingredients that go into a Bayesian analysis, the likelihood function and the prior. Think about that Bernoulli distribution that we were studying, where we're just repeatedly sampling out of Bernoulli. The Bayesian's answer, depending on the likelihood, it looks like something that does converge to normality as n gets big. And if you're a delta method type of person, you might immediately jump to the delta method and say, well, asymptotics, you know, if n is big, then my delta method argument, and I assume that whatever my test statistic is that I'm trying to estimate is normally distributed. For the Bayesian, when we were looking at the likelihood function, is that when n was relatively small, you saw likelihoods that were incredibly unnormally distributed, i.e. there are beta functions, or beta densities. They look like that. And so if we use the conjugate prior, a beta, then we get back an exact beta back. And it's fully conditional on the sample. And so we're not making an asymptotic argument about the distribution. I like that. So it does converge to normality, but if I didn't know that and I had small n, I would still do something that's reasonable. But if I were using an asymptotic argument and n wasn't big already, big enough to use the thing and I didn't check, you might just be reporting junk. So hopefully a reviewer of your paper doesn't catch that and ask you about it. So the answers are fully conditional. I like that. I like that likelihoods automatically utilize the sufficient statistics. So if I don't know what the sufficient statistic is, but I'm using a likelihood function, it's automatically in there. So if I thought about the Bernoulli example, I could be working through product of p to the xi's times 1 minus p to the 1 minus xi's, or I could be working with the function p raised to the sum of the xi's times 1 minus p n minus sum of the xi's. Sum of the xi's is the minimal sufficient statistic. The xi's are still sufficient, and so the only difference between those two functions is how much computing I do. So in terms of the minimal sufficiency, that can help me in terms of computing things fast, but in terms of our inferences and the properties of the inferences, it's only required that you condition on the sufficient statistic. So of course you want to use the sufficient statistic. It has all the information about theta. Later in chapter 7, we'll make formal proofs about that statement. That if you're doing an analysis not based off of the sufficient statistic, you can be beaten. And what that usually means is you can drive down the variance of the estimators that you're giving people. So if you're not using the sufficient statistic, the variability in that estimator is usually high. And you can drive down that variability through the sufficient statistic and basing your inferences off of sufficient statistics. Likelihood functions do that for us automatically. So they contain the sufficient statistics and they're fully conditional answers. So that's the whole idea here. So there's also another thing I like about likelihood functions, that if theta itself was high dimensional, then I have a joint relationship between all of the parameters already built in. So if you think about, if you're trying to infer maybe the variance and the mean from a normal distribution, if you weren't doing a full-blown likelihood-based analysis, you might say, well, I've got x bar and I've got s squared, and I can show that they're independent of each other. So, and maybe I can derive some properties out of that. But in terms of a likelihood function, mu and sigma squared are not independent of each other. They have a relationship. So if you just look at the kernel, e to the minus 1/2 xi minus mu over sigma squared, and that squared, you'll never be able to untangle the mu from the sigma squared. So mu and sigma squared are certainly not independent of each other. They have something to do with each other. But x bar and s squared are independent of each other. I like utilizing the joint relationship. So if I'm trying to come up with bounds on these things, it might make sense to come up with joint bounds that adheres to their joint properties. Likelihoods force you into doing that. So it might be convenient to treat everything as independent and come up with test statistics that are independent. But in terms of quantifying where you believe parameters live, we probably should use their joint dependency on each other. So I will say, if you're like a quality controller and you're always monitoring x bar and s squared, if you want to improve the power of your analysis, do a likelihood-based analysis and go crush everybody. So what does that mean? And I pick up like a percent or something like that. So, okay. We like likelihoods because they give us conditional answers and they automatically condition on the sufficient statistics. So there's two principles built in there. Likelihood functions give us estimators that adhere to the sufficiency principle. So that's automatic for us. So if we are doing likelihood-based analysis, we follow the sufficiency principle. That's a great thing, so we don't miss out on anything. I will also mention, likelihoods also contain all the ancillary information. So we're conditioning on x. X has everything in there. You can form any statistic out of it. So it's conditioning on everything. If there was a complete minimal sufficient statistic, we would be using it. So if we were using a likelihood function. So that's probably why I don't care about some of this stuff, is because I like likelihoods already, and so all of this stuff that I enjoy, the sufficiency principle, and maybe what's called the conditionality principle, I get it for free by using a likelihood function. So the conditionality principle says you should condition on your fixed data set. And so you shouldn't be doing asymptotic statistics and looking at what happens if n goes off to infinity. So we're not going to touch the conditionality principle anymore. The contention is people thought that they could derive the likelihood principle by saying it is the thing that you have to follow if you subscribe to conditionality and sufficiency. And it turns out there is no proof of that statement. People have tried to prove that, and there's always an error in the proof. People have tried to disprove it, and there's always an error in their proof too. So it goes back and forth, and it's been going back and forth since the 60s, when Birnbaum first introduced the likelihood principle. So there's no proof for this statement, but it seems like there's good reasons to like likelihoods. So here's the likelihood principle. So consider two data sets. They could be the exact same data sets, but your conceptualization of the data set, i.e. the probability distribution that you're assuming that it follows, might be different. I'll say more about that through an example in a minute. Maybe not a minute, but maybe 48 hours in 2 minutes. So consider two data sets, I'll call them X and Y. So they don't even have to be the same sizes. In the example that I'll give you, they are both the same size as the data sets, but they don't have to be the same. And if this statement is true, if likelihood given X is going to be equal to some constant that doesn't depend on theta, I'll finish writing this. Likelihood conditional on Y, if this statement is true, really all this says right here is if this likelihood is proportional to that likelihood. So this is just some constant out in front. So this statement is just saying, i.e. likelihood theta given X is proportional to likelihood theta given Y. i.e. you have the same likelihood function. That's what this is saying. So likelihoods are only defined up to a positive constant. I can raise them in height, the whole function. It's still the same likelihood function. So this is saying if you can construct two likelihood functions that are proportional to each other, i.e. they're the same likelihood functions, then inferences based on X should be the same, say identical to inferences based on Y. So what this is saying is if two people have the same likelihood functions, they're studying the same problem, the parameters they're studying have the same meaning, and those likelihood functions are the same as each other, they should come up with the same inferences. That's a strong statement. So there is no proof of this statement, and it's missing a key ingredient. It's missing the part of saying how you even do your inferences in the first place. So if you are a Bayesian, and you're thinking, oh, this is good because it's saying anybody that doesn't use likelihood functions are going to violate this sort of principle, and I do that. And so I use likelihood functions. My buddy down the hall uses likelihood functions. We have the same likelihood functions, so we come up with the same inferences. There's another piece to all of that, is what is your prior? So the key assumption here when Bayesians make this statement, i.e. you're violating the likelihood principle, it's making the assumption that we use the same priors for all the same reasons. And that's not true. So if I used a different prior from if I had data set X, somebody else had data set Y, we were trying to infer theta, we thought theta meant the same sort of thing, we did 2 different experiments, collected 2 different data sets. If we're going to come up with the same inferences, it means that we're going to follow the same inferential paradigm. And so, and there's no law saying you have to follow the same paradigm. So it's not telling you what you actually do with the likelihood functions at the end of the day. I think that's what makes this so contentious. So you can't actually prove this statement. So I'll just put it in quotes and say they should come up with the same inferences, they have the same information, but it turns out people do different things for different reasons. So we'll come back next time, we'll study the famous binomial, negative binomial example, and show what goes horribly wrong with p-values. So really this thing is set up, this statement, I think it's set up so that you can argue against p-value based analyses. And I do make that argument all the time. So there's some p-values I like and some that I just won't tolerate. So, and I'll show you one that I won't tolerate in 2 days. So review session tonight, and then we'll come back around to this and we'll look at an example of what can go wrong if you don't follow the likelihood principle. Good, thanks, you guys.